Do you know that you can use Fibonacci numbers to convert miles to kilometers and kilometers to miles? For example, 2 miles is about 3.21 kilometers, which is about 3, which is the next Fibonacci number after 2. 3 miles is 4.82 kilometers, which is about 5, which is the next Fibonacci number after 3. Similarly, 5 miles is about 8 kilometers, 8 miles is about 13 kilometers, etc. And to go from kilometers to miles, you have to use the previous Fibonacci number. So 2 kilometers is about a mile, 3 kilometers is about 2 miles, 5 kilometers is about 3 miles, and so on. There are 2 reasons for this. The first one is just a numerical coincidence in that the conversion rate between miles and kilometers is very close to the golden ratio. In 1 mile, there is about 1.61 kilometers, and the golden ratio is about 1.61. And the second reason, which is a lot more interesting, is that the ratio of consecutive Fibonacci numbers are approximations of the golden ratio, so that's why they can be used in that conversion. And moreover, the limit as n goes to infinity of this sequence of consecutive Fibonacci numbers is the golden ratio. And the reason for that limit is the following. Here is the very definition of a Fibonacci sequence, and if I divide throughout by fn, what I get is a ratio of consecutive Fibonacci numbers is equal to 1 plus the reciprocal of a ratio of consecutive Fibonacci numbers. Now, that sequence has a limit. I'm not going to prove this. I have proved that before in other videos. It's a little bit more involved, but let's just assume that the ratio of consecutive Fibonacci numbers has a limit and then compute what that limit is. And then if the sequence has a limit, then we can use the expression we had before and let n go to infinity. This is a ratio of consecutive Fibonacci numbers, so it will go to L. And this is the reciprocal of a ratio of consecutive Fibonacci numbers, so it will go to 1 over L. And so what we get in the limit is that L is equal to 1 plus 1 over L. And if I multiply throughout by L, then I get that the limit L satisfies L squared is equal to L plus 1. And now I can use the quadratic formula to show that L has to be 1 plus or minus the square root of 5 divided by 2. And all that remains is to show which one of the 2 is the actual limit. But the sequence itself is all of positive values, and 1 minus the square root of 5 divided by 2 is a negative number. So that cannot be the limit, so the limit has to be 1 plus the square root of 5 divided by 2, which is the golden ratio as we wanted to show.